This problem illustrates the use of the PG model. So in this problem, a gas is being compressed. A gas inside this piston cylinder device is being compressed in an isentropic manner. Isentropic manner means entropy remains constant. Initial volume is given, final volume is given as by a ratio of 10. The gas is being compressed. We have to determine the mass of the trapped gas, final temperature, etc. So let's begin by calling these two states, state 1 and state 2. And let's list what is known about state 1 first. The pressure has been supplied. Temperature is known. And the molar mass is given. Also, the volume is given to us. So let's do first thing first. You probably recognize just from the molar mass that it's probably air, but we cannot just assume that. So let's find the mass of the gas, which should be very simple. We can use the ideal gas equation of state, which is PV equals RT. That defines an ideal or perfect gas. So if you recall, R is what? R bar over M bar T. So therefore, the specific volume can be found as R bar over M bar T over P. What is R bar? That's the universal gas constant, 8.314 kilojoule per kilomole Kelvin. It is always the same number for any gas. And M bar is 29. By the way, R is R bar over M bar. So if you do the calculation, you can show that R turns out to be about 0.287. And temperature is 300, pressure is 100. So 0.287 times 3. And that gives us a specific volume of approximately 0.86. So therefore, the mass of the system is what? Density times volume, and density is inverse over specific volume, 1 over 0.86, which is 1.162 kg. So we are done with the first part of the problem. We'll verify all this once we finish the manual solution. We'll use test solution to verify. Okay. So now let's go and look at the other part. So we are done with what we are done with here. We are done with part A. And the second part is the final temperature. Third part is the final pressure. So we notice that if the entropy remains constant, let's write down what is known about state 2. Of course, mass will never change. M2 will be equal to M1, 1.162 kg. The volume is supplied. How much is the volume? Let's not write the suffixes because it's clear under state 2. The volume is 0.1 meter cube, which is 10th of the first initial volume. And of course, it's isentropic, so S equals S1. So this is essentially 2, 2, 2 here, state 2, how they relate to state 1. Now, for the PG model, if entropy remains constant, if you go to your formula sheet, let me just go to test and tell you what I mean by that. If you go to property tables, and table J has all your formulas that you ever need. So open up, this is table J. If we click there, it brings up a PDF file. I suggest you print that out. It has all the governing equations for different kind of systems. And here, this is what we're after. This is called different the equations for different material models, and we're using the PG model. So if you use the PG model, you will notice that, let me see if I can find a pencil. For the PG model, if entropy remains constant, this is the formulas for finding delta U, delta S, delta H, etc. But a special case happens when delta S equals 0, S equals constant. As you can see, then the ratio of different properties are connected by K, where K is the specific heat ratio. Okay, in this problem, we know the volume ratio. So notice the first equation, we can find the pressure ratio, temperature ratio, etc. So pressure ratio is connected to volume ratio by this formula, if you notice. So we'll just pick this up from here and go back. So let me erase this first. I think that will erase everything. Let's go back to our solution, and we use this formula now. So what is that formula? We picked up from table, we'll call this table J, the equation sheet. P2 over P1 equal V1 over V2 to the K. And the value of K has been supplied in this problem. If you go, the K is 1.4 is supplied right here. So we come back and we notice that P2 over P1, from this equation, we can find P2 to be P1 times, and V1 over V2 is nothing but 10. The ratio is 10. So it's 100 kPa into 10 to the power 1.4, and that's 2512 kPa. So we found the final pressure. Let's say the next question is find the final temperature. To find the final temperature, we notice that we can always use, let me use a new page. We could also go back to table J and pick up a relationship between, let's say, T2 over T1 is a function of V1 over V2 to the something. And from there, we could solve it. It's easier now that we know what is P2 over P1, which is 10 to the 1.4, which is 25.12. So we know the ratio of pressure now. So therefore, finding the ratio of temperature should be easier. And for that, we just write down T2 over, let me pick up the thicker pen, T2 over T1, or I'm sorry, let's first write down the ideal gas equation of state for this must be always true, and this must be always true, right? This is for state 1, and this is for state 2. Dividing each other, we can get P2 over P1 equals T2 over T1 and V1 over V2, right? Because mass remains constant, we can write that as V1 over V2, dividing by mass in both numerator and denominator. So therefore, it is T2 over T1, and that's 10. Oh, sorry, we want to find T2 over T1. So this equation means T2 over T1 equals P2 over P1 divided by 110, which is simply 25.12 star 0.1, 2.512. So that gives us T2, 300 times 2.512, which is, you can show that this is 754 Kelvin. So we have found the final temperature and final pressure. And the final question is find the specific internal change in delta U. Well, delta capital U. So it should not be specific. That's wrong. We should call it internal energy, the total internal energy. Specific will be small u. So with this correction, let's proceed. What we want to find is delta U, which is U2 minus U1, or mass doesn't change, so therefore it's U2 minus U1, which is mass times CV times T2 minus T1. Again, this is from table J. If you go to table J, we'll see that immediately, and I'll again take you back there and show you. But now our task reduces to, we already found T2, we found T1 is given, mass is given, to find CV. However, the CV is not given. What is given is K, which is Cp over Cv is given to us, which means Cp equals K times Cv. So our goal is to find Cv. And what else is given? K is given to us and R is given to us. We also know Cp minus Cv equals R for ideal gas or perfect gas for both PG and IG model. This we should always remember. Again, this is available in formula sheet. So if we substitute this here, we get K times Cv minus Cv equals R. That tells us Cv equals R divided by K minus 1. Recall that we already found R as 0.287 and K is given 1.4. So that gives us a Cv value of about 0.718. Now substitute this Cv in here and we get delta U equals mass. How much was the mass given to us? We did find the mass, I'm sorry. Mass was found to be 1.162 kg. 1.162, and Cv we just found 0.718, and temperature difference is 754 minus 300. If we substitute these values, we get about, if you do the calculation, we get 379 kilojoules. So we got all the manual answers, but you should never be satisfied unless you find a way to verify. One way is to go back and recheck every calculation. We'll follow a similar, because test calcs are available, we'll use them. But before that, look, in the table, the formulas I used should be in here. I used the formula delta U to be Cv minus delta. I used this formula. Also, I used Cp minus Cv equals R. And I also used K equals Cp over Cv. Actually, I derived this, but you can just pick up. The material properties are connected by this. I showed you this formula, but it's already here. So in this problem, R is known, K is known, so Cv could be found. Okay, now how do we verify all these? For that, we go to test calcs and launch, let's say, it's a system state, and we launch the PG model. Come here, and we have to always allow Java, and then we get started. In general, a gas, if you know that a gas, then instantly we can do a calculate, and you can see the material properties, molar mass, Cp, Cv, etc. are known. But in this case, we don't know what the gas name, so we select custom. And then write down the material properties we know. 29 was the molar mass, and K was given 1.4. Note that two material properties is sufficient to find others. You cannot enter anything more. If you do a calculate now, it found Cp and Cv. It's pretty close to what we found. We thought, well, anyways. Now, state 1, let's go out and calculate 100 kPa, and 300 Kelvin. And the volume was given to us 1 meter cube. We hit the enter button, and sure enough, you can see that we did calculate the mass correctly. And we also calculate the Cv here automatically. So let's go and calculate our state 2. To do so, we go to state 2, still. Okay, so for state 2, we can enter molar mass, or we can just write it as equals mm1, and of course K equals K1, and that should calculate the molar masses for us. Wait a minute, I think I made a mistake here. It's mm1, not mm. Okay, there we go. And what else we know? The volume, of course, the mass doesn't change. It's closed system, and the volume is 1/10 or 0.1. But I always like to write the in an equation form. That way, later on you can change things very easily. So if you click on calculate, the state is not yet totally calculated because we need another property, in this case, which is entropy remains constant, S2 equals S1, and that will give us the final pressure 2511 and final temperature 753.6, very close to what we got. Just out of curiosity, you'll notice that if you draw the TS diagram, state 1 and 2, as you can see, they are, if you draw constant pressure line, I mean, just like as you expect, 1 and 2 has the same entropy and the temperature is increased. More of this later on, but at least we have solved the problem and verify. Oh, by the way, the delta U, to find delta U, we go to the IO panel, and we can write an equation equals M1 star U2 minus U1, and that will give us delta U 377.97 or 378, and what we got manually was 379, very close. So go ahead and try to solve similar problems. In this case, although we have solved the problem involved assuming entropy equals constant, you can see that we can go use the PG model formulas to calculate delta H, delta S, etc. given two states in terms of pressure, temperature, etc. I will stop here, and we'll revisit this problem when we solve a closed process problem in chapter 5.